So yeah, I'm going to talk about ConvNet on graphs. And first, I like to say this is a joint work with Michael, Pierre van der Geest, Michael Bronstein, Federico Monti, Ron Levy, and Thomas Laurent. So I'm gonna talk about ConvNet architectures. So first, I will introduce the original ConvNet architecture. So just to make easier the transition to graphs. And then I will introduce spectral ConvNets for fixed graph. And in the last part, I will talk about ConvNet architecture for graphs with variable size and connectivity. So you see what I'm going to do actually is I'm going to relax the data domain from something which is very well structured, you know, which has directions like up, down, left, right. And then first I'm going to relax that to an arbitrary graph with no specific direction. But it is a fixed graph, and then I will have variable graphs. Okay. So let me start with the standard ConvNet architectures. Okay, so we know that ConvNet, this is a breakthrough in computer vision. So this is basically what the change of paradigm from handcrafted feature to hand-to-hand learning systems. But it's not only in computer vision, it's also in speech recognition, and also in language translation. So basically, this is an architecture that can learn high-dimensional learning problems. Okay, and we know this is high-dimensional data because of the curse of dimensionality. So if you take an image, for example, like 512 by 512 pixels, so the dimensionality of this data is 1 million. And if for each variable you take 10 samples, so it means that the space is going to be 10 to the power 1 million points. So that's very huge spaces, so it's like impossible, you know, to fill the space. But still ConvNet, they are powerful enough, okay, to solve these high-dimensional problems, you know, to find meaningful information inside these gigantic spaces. Okay, but there is something here. Okay, so as Jan said, so there is a very strong assumption about the data that we are using. So images, video, sounds, they look like to share a universal property which is compositionality. Okay? Compositionality means that they are form of patterns that are local, stationary, and multiscale. I will come back to that again to make the transition to graphs. And basically, ConvNet, it's a way to leverage this compositional structure, basically to extract compositional features and feed them to classifier, regression system, recommender system, visualization. Okay, so then you have a fantastic number of applications of that. So I call this, you know, the Swiss knife now of data science. You can do so much things. So. The key property of compositionality, so the first one is basically locality. We know that one neuron has a recession field which is actually local, okay, on a compact support. So, and we know that, and this is inspired by the human visual cortex neurons. The second key property is stationarity. So you can get global invariance. So basically you have like a big object, like a cat, and the object can be in the right part, left part. This is the same information. Okay, we have this symmetry. But here, what we are more interested in is also local stationarity. So basically, we have some patches which are the same across the data domain. Okay, like the yellow patches, the green patches, the red, the blues, and so on. And these are very important to create local invariance. So usually it's good because when you want to classify objects, usually your object in the same class can have some local variations. So this is a way to deal with these local variations. The last property is multiscale. Okay? So the idea is we start from simple structure and then we compose this simple structure to create a little more abstract structure, and then we keep going, you know, composing more and more abstract structures. Okay, so this is it. For the implementation complexity, so ConvNet, it's a linear complexity. Okay, linear complexity in the sense of the dimensionality of your input data. So if you want to create local filters, so basically this is going to be a constant number of parameters. Okay. For the stationarity, okay, this is the convolution you can use FFT, so you will get n log n. But usually because the kernel are compact, what you can simply do is to parallelize, the scan of your compact support across the image, and you will get a linear complexity. For the multiscale part, so downsampling and pooling, basically this is the order of the number of the dimensionality of your input data. Okay, so everything is linear, and this is the complexity. And then, okay, we can concatenate compositional layers. Okay, so these are our input features, like RGB for images, and this is our output features. And basically, it's just a series of pointwise nonlinear activation with some linear operator. So here, it's a convolution, and you can take ReLU. And the pooling can be done, using you can do median pooling, you can do mean pooling, and you can do max pooling. Okay, so usually max pooling is the one that is used. And in one slide, so this is all the nice properties of convnets. So you have, again, locality, stationarity, multiscale, constant number of parameters to learn per filter, and the learning cost n complexity. Okay? So the thing is, what is the data domain that we are using? So if we take an image like this one, and we zoom in, actually what we see is that we have a 2D grid, and on the top of the grid, we have some values, okay, like RGB. But this is fundamentally a Euclidean grid, and this is the same in 3D if you want to do volume. The same also for natural language processing. So if you have a sentence, and you extract the sentence here, and you have a one-to-one mapping between, word and numbers. So basically, just a series of numbers that lie on the 1D grid. Okay, and the same also for sound. So here, what happens is that the domain that you use is very nice. It's a Euclidean domain. Okay, so and this is the reason why all this operation of convolution, of pooling, are very fast and well posed. But the thing is, not all data, they lie on a Euclidean space, okay? So if you take, for example, social network, the connection between users is not homogeneous, okay? And on the top of that, for each user, so for each vertex, you can have a lot of data, like images, sound, text. So the question is, how do you analyze this data given this heterogeneous structure? The same also for the gene regulatory network. So you have connection between the genes, and the genes are composed of DNA. So again, how can you analyze this kind of data? The same also for the brain functionality. So you have a structural connection, and on the top of the structural connection, you have functional activities. So how do you analyze this? And so on for computer graphics, chemistry, so with molecules, NLP, physics, and so on. So, but you see, the idea is we can use this universal mathematical representation that is a graph, and then on the top of the graph, we have the data, basically. And the question is, okay, how can we apply convnet for this kind of situations? So the assumption that we are going to do, again, and this is probably a universal assumption, is that we are going to say that the non-Euclidean data are also compositional, okay? And the question is, okay, so if they are compositional, how do you define compositionality on graph? How do you define graph convolution and graph pooling, okay? And also how to make them fast, like linear complexity, if you want to use it in practice. So let me consider the case of spectral convnet for fixed graph. This is the problem setting. So if we are going to consider one graph and only one graph forever. Okay, this graph will be fixed. And on the top of this graph, we will have a set of signals, okay, that we want to analyze using convnets. So here is an example. This is the brain structural network, okay, so it is fixed. It's not going to change. But still, we have different activation, different time series for each region of the brain. So depending if I speak, if I drive, if I do different functions, so I will get a different signal here. And I want to be able to, for example, to classify this signal, okay? So this is the problem setting. The same here, so what we're gonna do for this first part is basically, so we have the standard convnet. So the input is an image, okay, this is a signal SK, and the image is defined on the Euclidean grid, and then we can do, for example, classification. So this is the standard convnet, okay. what we will do here, we will make this modification is, okay, we will gonna change the Euclidean grid into a graph, a fixed graph, okay? And the input signal, it can be like a functional MRI signal. And we can do, for example, classification. Okay, so we need to redefine convolution on graph. For this, we are going to use a spectral graph theory. So this is actually old technique in mathematics. And for dot sampling, we are also going to use some old tricks from graph theory. So spectral graph theory. So first we need a graph. So we know basically what is a graph. So we have okay, nodes, vertices, and they are connected by edges. And then you can have some weight for the connection. And then what is the most important operator here is the graph Laplacian. So the graph Laplacian, basically, this is the linear heat diffusion operator on graph. So basically, if your function is smooth, the Laplacian applied to this function will be small, but if your function oscillates a lot, then the Laplacian of this function will have high values. Okay? And this is really the core operator of spectral graph theory. Everything starts from this guy. Okay? So in the continuous domain, we have only one definition, which is the Laplace-Beltrami operator. In the setting of graphs, we may have multiple definitions. So the most two popular are the normalized Laplacian and the random walk Laplacians. Okay, so from the Laplacian, I can do an eigen decomposition. Okay, so I can extract eigenvectors and eigenvalues from this guy. And these guys are known. They are called the Fourier basis functions, or the Fourier modes. So here I can rewrite the matrix by a factorization of the matrix of Laplacian eigenvectors, the diagonal of the eigenvalues, okay, Laplacian eigenvalues, and eigenvector. Okay, so this is well known. And the interpretation is, okay, what I want to do is actually, I want to build the smoothest orthogonal basis on a domain. So in this case, on a graph. Okay, so again, a good measure of smoothness is the Laplacian. So what I want to do is basically to find the function that is going to minimize the Laplacian. Okay, so I want to minimize this guy. Okay, and I have the orthogonality constraint here. And this is, okay, so this is the standard theorem. So the solution is given by the eigenvector of this guy. Okay, so this is standard. So if we look at this Laplacian eigenvector in the Euclidean domain, okay, this is very familiar. Okay, this is the standard Fourier basis, the sinusoids and the cosinus, and this is used for JPEG compression, for example. For the graph, it's more interesting. Actually, the Fourier modes, the graph Laplacian, they are related to the topology of the graph. So the first eigenvectors, usually, they identify the communities on the graph. Okay, so, and this is something which is called spectral clustering. So what you do basically is that you compute the first, let's say 10 eigenvectors of your graph Laplacian, and you apply k-means, and then you have, you can identify communities on the graph. So there is a large literature on that. All right, okay, so now I have Fourier basis functions. I can use that to decompose a function with this basis. Okay, so I can decompose my function f as a Fourier series. So I take my function, I project on my Fourier mode, okay, and basically I can do this decomposition. I can do the same on graph. Okay, I take my function f, which is defined on the graph, I project on the graph Laplacian functions, okay, and then I have a decomposition on f on this on these Fourier modes. What is nice is I can do everything in a matrix vector notation. So in one line of code, I can put the graph Fourier transform in my computer. Okay, so I just need to collect the graph Laplacian in one matrix, and I apply this to one function on the graph, and I just did the graph Fourier transform. And of course, it is invertible, so I can also go back by doing the inverse Fourier transform. Okay. So why I want Fourier analysis is because convolution is easier to do in the Fourier domain, right? For graph. at least. So this is a standard definition in the Euclidean space of convolution. So we have shift invariance, I will come back to that. But most importantly, we have the convolutional theorem. So basically, if we want to do the convolution of f by g, first what we do is that we do the Fourier transform of f, multiplied by the Fourier transform of g, and then inverse Fourier transform. Okay? So, and we have a very efficient algorithm by John Tukey. So this is FFT and log n. So in the discrete case, so when I have n elements, okay, so the way I can rewrite f convolved by g is by having this circulant matrix, okay, of the g's times the vector f. But we know that a circulant matrix actually can be diagonalized by the eigenvectors, right? So if I put the eigenvector here and here, I can diagonalize this guy, and the diagonal is going to be the Fourier transform of g. Okay, so at the end, I can rewrite this guy by one line of code with the matrix and the vectors. Okay, so what I'm going to do now is that I'm going to do the same thing for the graph, but it's not a definition. It's actually an analogy. I'm going to say, okay, I can do Fourier, I can do the convolution on the graph by analogy to the Euclidean case. So what I'm going to do is that I'm going to take my function on the graph, okay, do the Fourier transform on the graph, times the Fourier transform of g on the graph, and then I do the inverse Fourier transform. Okay, so it's an analogy, not a definition here. So in the matrix vector notation, this is convolution on graph. Okay, so this is the equation that I have before. If I do a little bit of computation, what I have is something I want you to keep in mind, is actually doing the convolution, is just doing, okay, I have the Laplacian, okay, that I apply to f, and this Laplacian I apply some spectral function. Okay, so but basically this is just applying the Laplacian to f. Convolution is applying the Laplacian to f with some spectral function. So this is not shift invariant. I'm going to show you that in the next slide. And the coefficient depends on the Fourier mode. So if you change your graph, this is not going to work. Okay. And this can be very expensive because you have no FFT, so you get n squared. So this is not shift invariant because of that. So if you want to move, for example, a Gaussian function on the Euclidean domain, so the shape will not change. But because on the graph, oh, you cannot see very well, but because on the graph, the structure is not homogeneous, so the Gaussian will change its shape, okay? But it's okay, it's not actually a problem. Okay, so I know how to do graph convolution. Now the second operation that I need is to do graph downsampling or graph coarsening. So when I need to do that, so this is exactly as the standard case, I want to pull together similar local features, because this way I will be able to create global invariants with multiple layers, like translation, for example. So here the challenge is the grid is not linear. It's really a nonlinear grid. So I will need to be very careful with that. I need to find like a nonlinear multiscale coarsening technique to basically respect the nonlinear structure of the grid. And I want to make this fast. So graph downsampling is the same as actually graph partitioning. Okay, so we have this domain of the data. Okay, so this is the graph. I have some data on this domain. And if I want to do coarsening, what I want actually to do is I want to cluster this graph into meaningful commodities. Okay, so this is the problem of graph partitioning, and it's a very hard problem, so we need approximation to solve this. So balance cuts, so there is a large literature of graph clustering algorithms. So balance cut is a very excellent class to solve this kind of problem. So you probably know normalized cut by Shi and Malik. There are also normalized association, they are equivalent. And here what we use, actually we use heavy edge matching to do this nonlinear coarsening of the graph. Okay, so basically you have two steps. So at this level of coarsening, you take 1 point randomly, and then you try to find the neighbor that is going to locally maximize the normalized association. Okay, and then you create a super vertex, okay, that will be for the next coarsening level. You do that for all points, and you create a new graph, so a new adjacency matrix, and you keep going, okay. So here you have a guarantee to get a local maximizer of the normalized association, but nothing else, okay. So one thing, so when you apply the heavy edge matching, you will get an indexing of your graph. So you know for each vertex, you get a number, okay? You need to index it. If you don't do anything, the problem is that you will need to keep a table where you merge, for example, this vertex will be merged to this vertex at the next level. Okay, so you need to keep in memory basically all the matching between coarsen graph. So it's really not efficient. So one way to do this is to structure the pooling. So we don't change the topology. We only change the indexing. So we just do a binary tree arrangement of the indexing. So this way, if you look at two vertex, they're going to be merged at the next level. And I don't need to keep any table, okay? And I can do that in parallel. If I want to do 2-1 max pooling or 4-1 max pooling, I can do that in parallel. So it's a standard 1D grid pooling. Okay. Okay, so now I have the tools for graph convolution and graph downsampling. I can design spectral conv nets. So this is the first paper by Johan, Zaremba, Arthur, and Jan. So this is basically the inspiring and the reason why we are all this workshop today of trying to extend deep learning on graph. Everything starting here. So the idea is what I said in the problem setting. So you have the irregular grid, and now you want to change this to an arbitrary graph. And then you want to extract compositional features. So in the standard case, what you will do is that you will learn filters in the spatial domain. Okay. Here, what we will do, actually, we will learn the filter in the spectral domain because it's easier to do for us. Okay. So we don't learn in the spatial domain, we learn in the spectral domain. So we are going to learn spectral filter. So remember in image processing, when we want to denoise image with noise, we know that the noise are in the high frequency. So we design spectral filter which are low pass. So this way they will kill the high frequency and we will denoise the image. Okay, so this was for denoising. Here, depending on the application, if this is classification, regression, anything, given the data, given the application, this will be learned, okay, by propagation. So we let the data decide for us what are the best spectral functions. Okay, so now we need to take care of some limitation. So the first one is we need spatial localization. Remember that's very important if we want to have local variability for objects in the same class. So if we want a local spatial localization, what we need actually, if we use the Parseval identity, if k is 1, it's going to be the variance. So if we want a low variance, something which is localized, it means that the derivative will be small. Okay? So we need smoothness. Localization in space means smoothness in the frequency domain. Okay. So what we can do is, again, what we can parameterize the spectral filter by smooth basis function like splines. And then what we need to learn actually the coefficient of the spline coefficient, the spline coefficient, and we can also do that by propagation. Okay, so we are localized in space, and the number of parameters we need to learn per filter is actually a constant number, so this is the number of spline coefficients. Now we need to take care of the quadratic complexity to compute the convolution. So for this, what we are going to do is that we are going to parameterize the spectral filter by using polynomial of Laplacian eigenvalues. Okay. When we do that, we have two advantages. The first advantage is you can control exactly the support of your filter. We see that easily. So if you have a heat source okay, on the graph, so it's value 1 and the rest is 0, you apply 1 times the Laplacian, then the support is going to be increased by 1 hop. So 1 hop is basically all the points that you can reach with 1 jump, okay? If you apply a second time the Laplacian, then it's going to be 2 hop. So you can get an exact control of the size of your support. More importantly is that you can get linear complexity for convolution. How you see that is basically, so this is the convolution, okay, with f. At the end, you need to solve this sequence of operations, which are basically multiplying the Laplacian by a vector. But remember, the Laplacian in a real world, they are very, very sparse. Okay, so they can be very huge matrices, but they are really, really sparse. And for sparse graph, actually, the complexity, so this, the number of edges, is basically this is the dimensionality of your input data. And we can see that in the experiments. Okay, and one thing, maybe one observation is that, okay, the way we do the convolution, we don't need anymore to do the eigen decomposition of the graph Laplacian. We don't need to do eigenvector and eigenvalue decomposition. Okay, we just do Laplacian times a vector. So that's why it's computationally efficient. Okay, so now we still have this issue that this monomial basis is actually not orthogonal. It means that during the learning, if we change one coefficient, they are going to affect all the other coefficients. So we need orthogonal basis. So there are different options. So here we chose Chebyshev polynomial, which are orthogonal and which are stable under perturbation. Okay. So we still need to fix, and this will be the last part of the talk. You cannot transfer basically what you learn from one graph to a different one. Okay, so these are just sanity check on MNIST. So we build 8 nearest neighbor graph, and we just want to look at if we get something close to the original LeNet 5 architecture. Okay. So now I'm going to talk about the graph convolutional nets introduced by Keith and Welling. So this is a simplified version of ChebNet, okay, with an order. The polynomial order is 2. But what is very nice here, this is actually the first time where this kind of graph neural network have an impact, okay, on application. So this is the semi-supervised clustering problem. So you have communities, and inside each community you have one label, and you want to infer basically all the communities, okay? And here, if you use these techniques, then you have a huge improvement by 6%. So that was really the first successful application of this technique. Okay, so KylieNet. So as I said, the choice of spectral filters are not, limited to some basis function. So you can get a richer spectral filter. So Federico Monti will talk about this in the next talk. And also here I only talk about one graph, one fixed graph, but actually you can extend that to multiple graphs. But still they must be fixed, okay? And also Federico Monti will talk about this in the next slide. Okay, so for the last part, I'm going to talk about ConvNet for arbitrary graphs. Okay, so let me resume. Summarize what we did. So we started with the standard ConvNet. So we have a Euclidean grid, a lot of structure with directions, and it's fixed. Okay. Now we relaxed actually the directional information. We don't have any specific direction here, but the topology is fixed. Okay. So we can use spectral graph ConvNet to basically define a very rich family of filters, okay, to extract information from the signals. So that's because basically with spectral techniques you can take advantage of all the geometry of your graph. So that's pretty powerful. Now the question is, what happens if I change only one edge? Okay, if I change the topology of the graph, so I go to some variation of the domain. So can we still use spectral graph ConvNet? Or the question is, can we transfer, okay, the filters from this graph to another graph? And, and actually, in the general sense, no, we cannot do that. The generalization is not going to work. The problem is that the Fourier modes are actually not robust to perturbation. So if you change, and you see that, I mean, if you change one edge, you change the topology of your graph. Okay, you can get very different topology. So, and you can see that also with this equation. So if you have two graphs, G1 and G2, and this is your Fourier modes, then this is one spectral filter learned from one graph, and this is one signal, okay, and this is the same signal on the new graph. So usually you don't have equality, okay. You have equality when the two graphs are very close to each other. If they are very close to each other, then you might be able to transfer, but we need to be careful. So the problem is, okay, maybe what we should do, we should try to align the Fourier modes. But aligning the Fourier modes, it's like actually solving, you know, the graph matching problem. So that's very hard. That's very hard problem. So there are literature about doing that, and it's even harder when the graphs are very, very different. Then the Fourier modes are very different to each other. So the comparison, it's hard to do. Directed graph, so there is no clear definition of the graph Laplacian for directed graph. So Michael Bresson and his team has a new work about this. But it's not really clear. So Fan Cheng, she has some definition, but yeah, it's not clear on how we can use that. And also, so with spectral techniques, we assume that the size of the graph is fixed. So how can we deal with variable size? So we have this new problem setting. So remember the first one, the spectral coordinate. So we have one graph which is fixed, and then we have a lot of signal on this graph, and we want to analyze this graph using coordinates. Now this is the new setting. So we have okay, some graphs, and on the top of the graph we have some signals, okay, and we have a bunch of that, like molecules. And how do we apply coordinate to analyze, to do classification, to do regression, okay, all the standard techniques. So the framework to do that is actually given by Scarcelli and his collaborators in 2009, and it is called graph neural network. So this is a spatial neural network techniques that can deal with arbitrary graph. And the idea is, okay, what is like the minimal inner structure you will need, okay, to design neural networks for arbitrary graphs. So first what you want is, you want to be invariant by vertex reindexing. So basically you don't want, you know, to solve the graph matching problem each time you have a new graph, okay? So you want to be invariant to that. Then you want locality. So remember again, locality is very important for discrimination. So only the neighbors must be considered. You also want to have weight sharing. So basically you will apply, okay, convolution between the neighbors. And you want to be independent of the graph size. So this hidden vector is like, I would say, the most generic equation, transfer equation you can do from the neighbors to the core, to the central vertex. And the question is, okay, what is the instantiation of F? What is this guy? So in the original paper by Scarcelli, they use the multi-layer perceptron. Okay, so basically they are going to sum over the neighbors, okay, using multi-layer perceptron. In the recent paper by Lee and his co-author, they use actually, for F, they use the GRU cell. Okay, they use the GRU cell to do that. And, okay, so this is the recurrent neural network architecture. And then you can also consider the graph, the coordinate architecture. So, Suk-Bata, Arthur, and Fergus, so they introduced in 2016 what they call a vanilla graph coordinate architecture. So basically, okay, a very nice property is to have actually multiple layers. So let's consider, okay, these multiple layers, okay, this is the next layer, and let's do a vanilla definition of the convolution. Okay, so we take the central vertex, and then we take the neighbors, and we do the convolution on that. Okay. So, so this is going to be also a talk by Suk-Bata on Friday with the application of multi-agent communication. Okay, so when I started working on that, then when I look at the literature, actually the common trend, 90% of the paper, they don't use ConvNet to solve this kind of problems. They use recurrent neural network. And so I was wondering actually if there was something special about using recurrent neural network, because the complexity of the learning system is higher. I didn't know exactly. So what we did a numerical study to compare both graph architecture on a very too basic and representative graph learning problems. So we use first subgraph matching. I will come back to that. So it was introduced by Scarcelli, and semi-supervised classification. And also along the way, so we also added some inner structure to this graph ConvNet. So when you are on a graph, something which is very natural and that baked from Thai, Socher, Manning, Marchigani, Titov, basically is to say, okay, sometimes on a graph, you want to stop the flow of information. So if you have two communities, sometimes you would like to stop, the flow of information between the two communities. You want this to stay in the same community. And sometimes you want the flow to be open, okay? So you need some gates. So here we added the gates, so it's not new, it's just a very natural way to do that. And you also add anisotropy to the system. Because the spectral, for example, the spectral filters, they are anisotropic filters. So they don't care, okay, which vertex in the neighbor is considered. So here you can add back some anisotropy. And you need to learn again, of course, these parameters. All right, so this is the first graph learning problem we consider. This is, I would say, the most basic problem in graph analysis. So you want to do pattern matching. Okay, so you have some patterns like this one. Okay, and you have some value on the top of the pattern. And you embed this pattern in larger graphs. So here we use a stochastic block model, okay, and they are all different. So different connectivities, different size, and we want to be able to identify, okay, this original pattern. What you see here, so the x-axis will be the number of layers, okay, and here this is the accuracy. So the higher the better. So if you don't have to. And we also add residuality. So what's important is also to have residuality, especially for arbitrary graphs. You really get a big improvement. So what you see is that for a small number of layers, the recurrent neural network architecture actually are better. And in the literature, what we see is that actually people don't use too much layers. They use maybe 1, 2 layers, but not much. So that's why recurrent neural network are used. But if you apply ConvNet and you use residuality and you increase the number of layers, then you have a monotonous increase of performance of all the ConvNet architecture. So yeah, I forgot to say that all the solid lines are ConvNet architectures, and the dotted lines are recurrent neural network architecture. So at some point, their performance, they decrease. Okay, they are too much stuff to learn, so the performance decreases. And this is the time that you need. This is batch time. So when you use ConvNet, it takes less time than if you use recurrent neural network. So we also use that for the semi-supervised clustering problem. So again, you have communities, different size, different topology, and we give only one label inside each community, and we try to infer all communities. So we have the same conclusion. So if we don't use too much layers, okay, so the recurrent neural network will do better. But if you use more and more layers, then again you have this increase of performance of ConvNet, and also you will learn faster. So this is the accuracy, and this is the time. So you learn faster than recurrent neural network. So the conclusion is, if you have arbitrary graph, actually we should use ConvNets with a lot of. We should stack that with a lot of number of layers. And there was also one question from the referee. Say, okay, can you compare this learning technique for semi-supervised clustering to something which is a variational, a well-known variational technique? So when we use only one label, okay, for each cluster, actually, so the performance is for the learning technique 82%, and for the non-learning technique is 45%. So there is a very huge gap. Actually, we are surprised there is a huge gap of performance, and the test time is better because here you need to solve This is the number of edges, by the way. Here you need to solve a sparse linear system of equation. So it takes more time. Okay, so I think, yeah, I'm right on the time. So, so the conclusion is, okay, we have now different architecture, okay, to apply convnets to different data domain. We can still keep, you know, the properties of localization. We have linear complexity. We can do GPU implementation, rich expressivity of the filters, multiple arbitrary graph. And now I think it opens, you know, the path to application in different fields like molecules, for example. Okay, so there are some papers, some codes, and thank you very much.